So as I hope you have seen before, I'm in the Topos Institute now, and that kind of gives me the chance, let's carry on with the propaganda and saying that one of the things that I actually like about being in the Topos Institute is that I can always put this lovely slide with our mission. So we shape technology for public benefit by advancing sciences of connection and integration. And our goal is a world where the systems that surround us benefit us all. And for me, that's kind of quite important to be able to say these things, because for quite a few years, more than 20 years, I've been working in Silicon Valley, and in very different sorts of outfits. So the first one on top there is Xerox PARC, where I spent some 9 years of my life. Then a collection of startups, and up in Samsung. In particular, my startup, Cool, was a very a momentous sort of experience. Was a startup trying to be a competitor to Google. As you might have realized, it didn't go anywhere, right? But you know, the reason I think I wanted to mention this business of background and of what I've been doing the last 20 years is because some of you kind of know that I actually kind of come from a very different kind of background. The guy over there on the left is Martin Hyland, who was my supervisor in Cambridge. I don't know how many of you know the guy in the middle, Robin Genji. And I hope everyone knows Alan Turing. And you know, I know it's a very old joke and stuff like that, but I cannot not say this business that makes me Turing's academic granddaughter, right? Because and the important thing about that is that Robin was the only person that Alan Turing supervised in his career, so there aren't that many of us around.
The Turing supervised multiple fathers.
It's true, yeah. And kind of the work that I did is based on the work of Kurt Gödel, and that's why it's called the dialectical categories and stuff like that. But I'm not, unlike the last talk that Joseph heard, I'm not talking about dialectical categories here at all. I'm talking about this idea of AI tools for mathematics, and I kind of, it's a very simple idea, an obvious idea, as you know, as obvious as it can get, right? You know, AI is going places. They are doing lots and lots of things, and their tools, the different systems that they have are kind of going so fast that you know you go to sleep and the next day there's 3 or 4 new systems that you could be thinking of using. So I want those tools to be used for mathematics, and so what I kind of wanted to discuss with you a little bit is why I'm talking about better mathematics, why do we need such tools, why do we want such tools that the guys have, and I want to talk a little bit about which AI and NLP tools, but this is going to be, and I'm going to show you 3 small prototypes, but they are very preliminary, and it's all about selling the idea, selling the program of doing this kind of stuff. And please feel free to interrupt or disagree or ask questions if you want. So, as I was saying, I'm going to start with better math for society. Because at Topos, we actually believe that the kind of knowledge that we are known for, kind of category theory, empowers people, and that the expertise that we all here have should be available to all. And that's being available to all is all very good, and we are doing very well on this front, because I don't know if you know, but we have more subscribers on our YouTube channel than the Institute, the AI2 Institute, which is the Allen Institute for artificial intelligence has less subscribers than we have. So we're doing some things right. But availability, and we, of course, apart from the colloquium, which several of you here talked at, Kevin did, Joseph did, lots of people, Jeremy did, you know, Steve did, Emily did. I think lots of you have talked to, Millie did, sorry Millie. So, you know, we are trying to make the stuff that we think is important available to lots of people, but availability is not enough. We actually need to make this stuff more accessible as well. We don't want people feeling that this is not for them. So what we want is modern AI and natural language processing tools to build accessibility tools. And that is good for several things. And this last link here is a blog post that we wrote initially about this idea of network mathematics. And it is a story that I think everyone here is very familiar with, which is this story. I mean, the story in the Quantum magazine in November 2019 is one of these things about people discovering new equations in linear algebra and thinking that they were kind of so easy and so obvious that they should have been discovered many, many years ago and should be in all the textbooks. And these were three physicists. That's why I'm calling Tao and the physicists. And the physicists kind of called, or emailed, or called Tao and asked him about it. And he said, no, it should be. I should know that, but I don't. And I don't think I've seen it anywhere. And then they kind of published this stuff. And as soon as they published this stuff and appeared in the magazine, 35 or 36 people kind of came up saying, but I published that from 1935, kind of in good places, not in stupid places. So what I want to make the point is that, you know, we all know about the horror stories about PhD students discovering in the eve of their examinations that the stuff that they've done had just, that they are presenting the next day for the defenses kind of had been done 20 years before somewhere else and stuff like that. So all these things are reasons why mathematicians need help, need tools to help them with this business of knowing what there is and if possible, more than just knowing what there is, kind of improving what they can do. And, you know, as I was saying earlier on, this talk is about propaganda. And I also didn't say, but it was presented in a place called Dilla, which is a special substack of the talks in Park. And so, you know, I kind of wanted to convince them that we, mathematicians, are in fashion nowadays, and I kind of couldn't resist using Jeremy's picture to show that we are, that things are going well for us. But I can be a bit more crass and actually use Jeff Dean, which I don't know if all of you know about Jeff Dean, but he's a big wig in Silicon Valley. He's one of the guys behind TensorFlow, and has been around for many years at Google, and kind of on this business of predicting the future and stuff like that. And as I say, even Jeff Dean is saying that math education is clearly deeply important for AI and more generally. And the guy who originally posted that on Twitter was saying, well, Elon Musk and Sam Altman may not agree on much of late, but they do agree that AI is built on strong math foundations. And so kind of that was what I was trying to tell the guys in Dilla, that strong math foundations are important for AI. And being even more crass than I just been, I kind of say that, you know, there's plenty now of calls for proposals and lots of grant money being distributed in this direction, in the direction of using AI and formal methods for mathematical reasoning, which is
in the United States.
Can I tell about anywhere else? I live there, right? That's.
Brussels is nearby, so if you can pitch this, it would be very
Well, I'm doing my best to try to tell to pass the message to everyone who will hear me. But going back to more, I mean, this was the bottom bit of the process. I wanted to say that we all know that that the problems that I was mentioning about mathematics are real problems. And what I don't know if you guys know, I only discovered some 4 or 5 years ago, is that in 1945, one of the directors of what is now the NSF, Valeria published this article in the Atlantic called As We May Think. And at that stage, it was all, I mean, you know, it's before Turing, before the existence of real computers, and he was already talking about the fact that there's a growing mountain of research. There's increased evidence that we are being bogged down by specialization as specialization extends. The investigator, instead of researcher, he talks about the investigator, is staggered by the findings and conclusions of thousands of other workers. And he's proposing something that is a little bit like the internet, or variations of the internet. I think it's worth reading. Because, you know, he was right in 1945, and he is much, much, much more right now, things got beyond the pale. So mathematics is growing exponentially, and we need more infrastructure for organizing and communicating results. We need to avoid wasted research time, we need to avoid duplication of research, and especially, we would like to not miss connections between fields. And for that, we need more collaboration, we need bigger teams, we need to move from the artisanal mathematics that most of us still do, kind of producing our systems, or, you know, not both computer systems and logical systems, or things like that, or theorems as such, or definitions, or books and stuff. We still do that, right? We produce something, we bring it to show to friends, and that's how it works. It's a bit like the Middle Ages, right? You take a little bit of bread to the market and you sell it to your friends. And what I say is that we actually need industrial mathematics if we want our mathematics to have an impact, which I think we do. And we know already that there's been talks of AI trying to read science papers predicting future discoveries. This is a little bit of an exaggeration, a little bit of the hype as usual, because what they showed was that, you know, that using AIs, they could show, in particular in the case of material science, they kind of proved that the new substances that have been invented kind of could have been predicted by the AIs 5 years before, if they kind of had, using the abilities that we have now of dealing with huge amounts of text and kind of correlate things and find tendencies and trends and stuff like that. But, and they did that also for, I'm sure you have seen it, for drug discovery and stuff like that. But the fact is that no one's doing the same for mathematics or for the math literature. And I think we want to do the same. So the question is how? So, as I was saying, this is a programmatic talk about network mathematics. And I think one of the things that we have a problem with is this business that mathematics is considered too esoteric, too hard, too difficult, too forbidden. So we want to make math more accessible to everyone, students, mathematicians that do not understand the person in the next office, interested lay people. And we want to make use of these incredibly fast improving NLP tools that we have now. And one of the things that we want to do that, so now I'm kind of start to getting on how I want to do this stuff, and I want to do it using language, using vernacular English, as opposed to the several interesting and different formal language that we have. So I want to kind of extract math concepts from texts and link them to ontologies, and I want to build a math knowledge graph. And I hope, but I don't have much evidence for that yet, but I hope that that would be useful for formalization in general. So I thought I was going to give talks in the third workshop, the one about bridging between informal and formal mathematics, but I'm happy to talk more than once. Okay, so what I'm going to show you now are kind of this first steps that we are doing, and the first step at all is a system that we call Parmesan, that extract math concepts from. You might not be surprised to know that of course I'm doing my stuff over category theory because I already know that better, and I liked it. So in particular, Parmesan works over the TAC abstracts, the NLab, and at the moment only on the textbook that Tom Lenses did and made available in open source in 2016. Then I want to talk to you a little bit about MathChat that uses ChatGPT and GPT-4 to extract, again, mathematical terms and the problems that we have with that. And finally, I want to talk about MathGloss, which is an open glossary of mathematics, kind of basically talking about undergrad math, because I think we all agree that, that a basic first degree mathematics is something that that should be accessible to any other people who want to know about it, and it should be a way that all the systems, proof assistants and theorem provers should be able to know how the other ones do that basic level, the first degree in pure maths or mathematics in general. So there are other projects that we are starting that are more sophisticated, but for the time being, I'm talking only about these three that have little prototypes. So the idea here is that, when you kind of try to read some mathematics that's not part of your normal style, you kind of, at least I do, I read for the gist, and I kind of mentally mark the things that I don't understand so that I can go and check it. And we think that if we can do this business of getting stuff from the literature and enhance it with this ability to look up certain concepts, that would be a very good thing. And you might say, but Valeria, aren't you talking about things that happened in the 1990s, the early 1990s? Isn't that hypertext and stuff like that? And it is similar, of course. But of course, in the 1990s, people were doing that by hand, when you build up your text, you put your links already. And I'm now saying that we should be able to just get whatever literature is there and do it automatically. Because if we could do that, then we can create personal indices of things that you should check automatically. It would make life of people who are writing books much easier, because the system would tell you all the things that you should have definitions for and stuff like that. And it's kind of a bit surprising that we don't, as such, have the technology for that so much. And so you're going to ask, But why is that? I mean, don't we have ChatGPT and all this wonderful stuff? And we do, but we don't have very good annotated data sets for mathematics. Because, you know, if you want to know what are the size of the, what's the height, the waistline, and the bust of Taylor Swift, it's very easy, and you can get lots of mechanical Turks that will annotate it for you all over the place. But if you want someone to tell you what's a parameterized adjunction, you know, you need someone with a special kind of background, formation, and stuff like that. And you're not going to be able to pay them 25 cents to annotate things for an hour. So one of the things that we will have to do something different to get that going. But the first thing is to look at what the linguists have for us, right? So what kind of stuff linguists have for extracting math concepts on their shelves already sitting? They have, and you know, that's the thing. I'm now talking to you as a linguist, a computational linguist. Linguistics guys, and NLP guys work on the basis of tasks. And they have this thing called a named entity recognition task. So, which is the stuff that says that Taylor Swift is a singer and Barack Obama was the president and stuff like that. And as I said, there are billions. If you look in papers with code, you're going to find hundreds of data sets for those things, for named entity recognition. Similarly for keyword extraction, and kind of similarly, a little bit, I mean, less so for definition extraction. Definition extraction is considered harder because you have to kind of have definitions for the specific areas. And as I was saying, you need corpora, and you need, if you're going to try to use whatever the linguists have already produced, you need to find which are the good tools for extracting your mathematical concepts. So the linguists also call it ATs, automatic terminology extraction, and there's no AT dedicated to mathematics. But there are kind of course several systems that we could perhaps put to good use if people like us wanted to have such a thing. So the first thing that we started doing, I mean, and this is with a good friend who is a linguist from Cornell, Jacob Collard, we started kind of collecting what they call corpora. The singular is corpus. So we have one corpus of abstracts of theory and applications of categories that goes up from 1995, because category theorists were one of the first ones to have this kind of open source journals, until 2020. Then we have the NLAD entries, and then, as I was saying, we have Tom's book, and all these things are processed with Spacy, which is one of the best and fastest systems available nowadays. But as I'm sure you all know, that one of the difficulties that we have, and you know, kind of Tim Gowers and Mohan Ganelizai, but you know what I'm talking about. Yeah, I'm not going to massacre his name more than I already did. They have this theory that mathematics is harder to do NLP over because it is actually what the linguists call a switch language. So, you know, you actually all the time moving between two different languages, English and the symbols of mathematics. So everyone has problems with what to do with LaTeX, and then we have Michael with STEC and stuff like that, but it's not, I mean, my proposal is very different. It's about using whatever people are doing already now, and kind of, so what we can do in this case is actually try to work with the LaTeX. That is the thing that all mathematicians use, as far as I'm concerned. And the corpora that we kind of started creating is very different from things like GSM, 8K, and the math data sets, because these things are mostly I mean, do you guys know about those guys, about this corporate GSN? That's it's elementary grade school mathematics, so up to level 8 of elementary school in the US, and math is just a pile of everything that they could find, but they are not corpora as the linguists called it. They're just collecting the things, and in particular they're about specific problems, and you don't there is a sense in which you don't want to learn from the text that 2 + 2 is 4, because you have better ways of learning that than actually using corpora of problems to tell you that. So these things are a different kind of corpora from the one.
Will you say what you did with BERT over the abstracts?
Sorry?
Will you say what you did with BERT, B-E-R-T?
Yes, but yeah, no. You know, the point here is to kind of use what the linguists are using, and but with its several different incarnations. I'm just using BERT for transformers. You know, there's nothing.
Yeah, I know what it is. I'm just asking what did you do with it? Like, how did you process the abstracts with the language model?
We just kind of do the parsing and cleaning of the text, because we are interested in the text itself. And we are interested in kind of doing the name it entity recognitions that they can do, so they still can tell us things like Grothendieck is a mathematician and Bern is a place, but when I was mentioning before that they don't do enough NER, I wanted entities that were kind of mathematical concepts. So I wanted topological space or vector space of complex numbers to be recognized as special entities. And that is what BERT does not do. There is, if you know about that, there are 2 versions of math BERT. Neither of them does that.
So you first pre-process it with BERT, and then you run it through the Spacey.
It's just, Spacey is a very fast and powerful implementation of a BERT model.
Okay.
I'm sorry. Sometimes I forget that it's not obvious. So, as I was saying before, the problem is gold standards, right? So checking baselines from what we did is hard because there are no baselines for extraction of concepts. So there's no human annotated golden standard, and there was a little bit of something that happened many years ago, kind of 2017 is a prehistory in this area, and that was about scientific concepts. So you'd expect it to be at least close to mathematics, but as I say, there was very little transfer in terms of machine learning between this small scientific corpus and what we can do in mathematics. So we tried, since we don't have golden standards, we tried silver sets, and we had very low results. So it doesn't work directly. So instead of desperately trying to produce the golden standards, because one would need to pay for that, and as I was saying, pay more than what the mechanical Turkers get, we kind of changed our tackle, and we kind of decided to let the users ask for concepts. So Parmesan is a kind of a math assistant that does entity linking. So it kind of, if you ask for a concept, it will send you both to Wikidata and to DN Lab, because we're talking category theory. And it does also collocation search. So let me see if I can show you. Yeah. I'm going to try something slightly dangerous. Let's see if it works. I have in here what Parmesan really looks like, hopefully. So can you give me a categorical concept to try?
Adjoint.
What?
You said adjoint.
Oh. don't do that. Don't do that system. So, what Parmesan does is kind of give you a knowledge base first. So it will show you that one version of adjunction being construction of a large algebraic field by adding elements to a smaller field, gives the one that I kind of wanted, the adjoint functor, and then gives you the nlab if you want more information. And what I was talking about collocations is that it then looks how the concept is used in specific corpora. So you can check what Tom has to say about adjunctions. And starts with a good one, free and forgetful. But has some issues with the LaTeX not being dealt as well as good. It's not totally bad. You can still see some. You can read it if you're desperate. But I'm sorry. I wanted to show that actually one of the things that we wanted to do here is actually to have it in different levels of knowledge somehow, because you want to have basic category theory, and you might even want to have something that's even more basic than basic category theory, but you also want to have whatever the nlab says, and presumably you want to have also the frontier mathematics, the things that people are doing. Well, I was going to say doing now, but it's actually only up to 2020. What STAC has up to 2020. So there's lots. I mean, this is a totally preliminary prototype. It doesn't do lots of stuff. It doesn't do fuzzy search. It doesn't do good relevance ranking. It's really very bad. But at least 2 students from Berkeley told me, because I asked them to do a collection of search, that adjunction wasn't the one that they wanted. They said that they find parameterized adjunction easier than they found in Google, because somehow Google had not indexed that or something. Who knows why? I mean, these things don't work, right? I'm just saying that the kids were being nice and they said that our stuff worked for them. So back to, come on. So that is Parmesan, and I was saying, the problem with this whole stuff in machine learning is how to evaluate your stuff compared to others, right? So we actually kind of took quite a little trouble comparing to the state of the art in 2019, the state of the art in 2021. I mean, because this paper has been doing the rounds, not that we kind of only, that we wanted to. TextRank and MWE toolkits are very old stuff too, but still used by people who need results fast. And as I was saying, there was very little transfer, and you can check the preprint to see how bad the situation is for mathematics if you just do things directly, like we're doing here. So we still want some sort of WordNet for mathematics, so we kind of found another team and decided now to go for the generative AI. And the team leader is Professor Moss from Indiana, Larry Moss, another category theorist, by coincidence. And here what we're doing is this business of asking ChatGPT and GPT-4 to extract the concepts for us. And that's something that I talked about in Kikham's last year. And the difficulty is to make sure that the concepts extracted are correct and as complete as possible. And as I say, it's not us mathematicians who have this problem. The guys who work with Old English have very similar problems because of the lack of annotated data sets. There's lots to be said here about how to apply their tools to our domain-specific field. I'm not going to go over it. One of the things that's complicated is to decide on annotation guidelines because, as we were saying a minute ago, I bet we don't know enough about, say, the mathematical physicists to annotate their kinds of papers. So you have to kind of take an approach that treats the math concepts as black boxes to a certain extent. And that's hard to decide how much of a black box or a gray box or a semi-transparent box you can go with. And we did a collection of experiments with smaller ones, big ones, and lab 55,000 sentences. And the problem is lack of evaluation. So we have a small tool that one I'm not going to show because it just helps humans. Just took a picture of it. It's the math concept annotator. So you take a sentence which you can't read now, but it says something like, this yields a quadratic algorithm deciding the quality of diagrams in the free double category. And the ChatGPT gives you a collection of terms that it thinks are mathematical concepts, and a human can kind of accept or reject these concepts. But still, you need loads and loads of very dedicated students to do that to the extent that we need to prove that this thing is working. So what we showed in this case was just inter-annotator agreement, which surprisingly is very bad for humans too. Humans had a hard time deciding when the same things were reasonable concepts. And so this is just what you can get out of it. It's not much. So I want to finish with math gloss, which is this idea that you want to connect glossaries or data sets in general, and that kind of, I think Katja is going to talk much more about that at some stage. But the idea here is that mathematicians have been using their computers for doing things in the areas that they are interested in. So the modular form guys have the LFMDP. There's lots of there's huge things on the OIES, the sequences that NIST has been paying for a long time. The category theorists have their lab and a few other, the one lab and a few other special repositories of knowledge. And I think we should have also repositories for simpler things. So one of the things that we have a problem with is this business that, as I was showing Parmesan, that you have many different mathematical audiences that you want to cope with. So what you need for an expert is not the same thing that you need for a newbie, someone who's just starting. And so then what we want to do is kind of help bridge the language gap between natural math and formal math. And I will try again to get into this one. Maybe not, maybe just kind of, yeah, maybe just show it. So the thing here is again, a very simple and direct idea. The idea is just that you're going to use weak data, few items, as your word net synset. You think of it as being the concept. So I kind of particularly like the 0-1 law that starts this table because it is something that the Lean guys have been doing for a while, and I think it's very clever. The top of the column is called France undergraduate degree, because the guys, or you guys, did this business. Oh, it was you, great. I mean, Johan told me about that. When he gave it, Johan also talked to the Open Institute, and we got talking, and he mentioned to me that there was this. And so what happens when you click on this 0-1 law is that it uses your mapping and goes directly to the place in the Lean repository where the concept is defined. And the other bits, I mean, of course, we have the NLab because I like category theory, so it's there. We have the dictionary of Tim Osgood, because it is doing translations manually. And we have Chicago notes, because you see, undergraduate degrees in the US are much more different amongst themselves than they are in France. So we kind of have only the Chicago honors, and because Lucy, the person who is actually doing this stuff, like young student who is about to start her PhD in Berkeley at the end of August, she kind of took her courses in Chicago and she kind of created these terms directly. So at the moment it's very, very small. We have only 906 terms. And, you know, our ignorance is kind of quite big, right? For instance, I don't know how many concepts one would need to have to cover reasonably well the whole of mathematics. I can tell you that the Encyclopedia of Math has something like 18,000 concepts. I can tell you that Wolfram Alpha has something like 13,000. I don't know, you know, I don't know, and I don't think anyone does either, how close the things align or don't align. So we kind of thinking of working more on that. So that's, and because these things are kind of always funny, I talked about that in Dutch too last year in October when Katja and lots of other people organized one of these meetings, and we kind of, I was showing exactly the 0-1 law, and the guys got cross with me because it was using, and still is using, mathlib 3 instead of 4. You know, nowadays if you go to the thing, it actually goes directly to 4, no problem at all. But I was, you know, one of the hard things here is keeping up to date, keeping the things going forward. There is at least one engineer totally dedicated to trying to make this pipeline that we are developing robust to updates. And that's just because he likes the idea, you know, not paying him anything. So we'll see if it works or not. So, as I was saying, the work is just starting, right? We have to expand the process of corpora mathematical text. We need to fine-tune BERT and spacing. Both of them are customizable. They need to be done. We can construct many more open source glossaries. And the idea on the math gloss is that you can substitute the columns for whatever is your special thing, right? So if you like the Langlands program, you can just use the LFMDB, and I've been talking to the guys about that. There is an issue in their repo at the moment about trying to do something like this. And as I say, there are good sources available because the mathematicians do enjoy what they do, and they kind of produce these things. My problem is just putting them together, kind of not trying to reinvent the wheel or rewrite things, but actually kind of use the guys who know about each one of the bits. There's also the other one that's the topology, the count of examples in topology. What's the name?
Paiva.
Paiva. So, you know, and I'm sure there's many more that we don't know, right? Kat has been trying to discover. But you know, we need to put all of them together to build knowledge graph for mathematics and complete it as much as possible. And the idea here is that we use the mathematical English as a lingua franca between the different formal systems, implemented or not. I think with that, I am going to, there's one warning here, which is this business that ChatGPT, I cannot prove the quality of ChatGPT, but as we all know, it's very easy to use it. So it will be used and misused and abused. So I think it kind of falls a bit on us to make sure that people don't misuse it completely for some things, because you know, I hope you've all seen this business of ChatGPT saying that 8 is a prime number, and then kind of saying, I mean, the things that the systems say are kind of, I mean, there's a whole industry now of ChatGPT and GPT-4 failures. Kind of, there's several websites and GitHub repos and stuff like that, just of the things that they kind of, because the thing is, it is very good, guys. It's very good. It's very impressive. So, unless you're looking at it and reading it properly, you don't see the mistakes. I mean, some of the stuff that the hallucinations are getting every time fewer and harder for us humans to detect. So I think that's the warning is this business that we need to measure the quality of the LLM's results for our own sakes and stuff. So what's next? Well, we have these 3 small parallel projects progressing. Each one has new milestones. I need more cooperative evaluation. And we have some new experiments on reasoning with math. And I will talk to anyone who wants to talk to me about it, but I decided not to even try to write anything because it's kind of too preliminary. So thank you.